Just to be clear, this is not about AI. There are connections, no pun intended. Yeah, hi. Okay, starting where? So I'm Alex. I'm a software engineer at Netflix. Sometimes I'm saying that I'm an ontologist as well. Maybe at the end you'll get a better idea of what it means. I've actually been doing that kind of stuff for a long time, not all the time, but I was very lucky in 2008 to work at the French National Library, the second biggest library in the world after the Library of Congress. And at the time it was about integrating a lot of very disparate data in one big knowledge graph. That was pretty cool. Later on, I was lucky to actually move to the US and join the W3C to work on some of those technologies directly, putting my name on some of the standards for that. I was the one who deployed knowledge graphs on apple.com as well. It was a pretty nice adventure. That's not the talk about it, but we can talk about it at the end. And then nothing for a while. And about a few months ago, I was already working at Netflix on the data platform, and I moved to content engineering, where, as you'll see later, there is a big use case for deployment of ontologies and knowledge graphs. Other than that, you can ask my wife. I'm a huge One Piece nerd, and I will never miss an opportunity to talk about One Piece. So, yeah, that's what we're going to do today. You can think about it as a journey in the world of knowledge graphs. So first, I want to give just deep intuitions about what this is all about. And little by little, we're just going to get closer to RDF, the resource description framework. And we see that in order to make use of all of that, we need to be able to talk about those things in a more precise way. That's where ontologies come in. And then once we have enough knowledge and terms that we can use and share in this room, I'll be able to finally talk about the problem that we're trying to solve at Netflix within my organization, and then at the end, wrap everything together with the upper ontology. So, all right, I gave it away. Nice. Yeah, so the starting point, all of it, like there was one thing that you have to remember with knowledge graphs. It's really, you have to be able to conceptualize what the graph is all about. Think about the nodes, think about the arcs, and what do they really denote? So that's called conceptualization. That's the most important word that you have to remember today. It's when you close your eyes and you're trying to think about a domain, and you're trying to say, what are all those nodes about in the graph? So think about the world of One Piece, right? So it's a crazy, crazy world. I don't know if you're into it. Like more than 1,000 episodes, manga, the same thing. You have thousands of, like 1,400 characters that are described. Some of them are marines, some of them are pirates. They can eat fruits, and they have those wonderful powers. It's just crazy, but in that gigantic domain, we're just focusing on this one guy. So this is not a picture of Luffy, the main hero. This is actually Luffy in the graph. That's really what the conceptualization process is all about. But it's a lot easier for me to talk about it by using the picture. And Luffy has quite a few friends on his adventure. The first two friends, so Zoro and Nami. And in this big world, we want to kind of categorize what they are. And in this case, I want to say that in the world of One Piece, I want to say that they are characters. So far, so good. It's just very, very simple. Like, we're just going with the ideas. We're conceptualizing everything. And each of these things, they have descriptions. Like, they probably have a name. Like, we need to identify them. They talk to each other. In this case, right, I want to say in the English language, that's their name. But this is actually coming from Japan. So, well, I cannot read it. It's probably the same pronunciation over there. But yeah, it's actually important to say that that same piece of data can be contextualized based on the language. And then there is something interesting as well that can happen. Some of the characters are, somehow, they can eat some of the devil fruits, and that's how they get some of the powers. So on the right-hand side, none of them ate any fruit, but Luffy actually ate the gum fruit, and that's why he can do this crazy stuff. Like he becomes like gum at the end. So, okay, we are building the knowledge graph for the one-piece universe. A few more things that we can probably say about the devil fruit. Same thing, there is a name. And in this case, we can say, oh yeah, but maybe there are some more specific fruits, like kind of a taxonomy of fruits. They are all a little bit different. We can organize them. In this case, it's a kind of paramecia. So we can see that the labeling can be a little bit more precise as well. Okay, so far so good. But if you give that to a machine, the machine would be like, well, I have no idea what you're talking about. This is just an image. So we need to apply the concept of conceptualization to machine. How can the human and the machine actually talk about the same thing? In order to get there, we need to make things addressable. Like, you've been doing that. You do that all the time. You don't even think about it. If you want to share something with friends or colleagues, whatever, you take the URL and you paste it in Slack or in your messages. Well, it's the same kind of stuff that's going to happen here. So how does it work? So that's our knowledge graph. So conceptualization, and we want to make things addressable. So we're going to start with Luffy, and we're going to say, yeah, maybe we can use that string. We can kind of have a namespace, and then within the namespace, we're going to declare that term, monkey_d_Luffy. Okay, and now I just want to make very small sentences that would represent the same kind of knowledge. So the graph would become something like that. You've never seen that stuff before, but I'm pretty sure that you can read and understand kind of what's going on. And that's really why this is actually pretty powerful. Okay, so we keep going. The next part is, how do we introduce, the most important part of the graph, connecting things? So we have Luffy, we have the gum fruit over there. Well, you know the recipe already at this point, right? We need to define the token, the term within the namespace, and then we can maybe connect things. Okay, so we just introduce the new term and we connect things. Pretty easy. And then finally, we wrap everything together, and then we see, yeah, that looks pretty equivalent. I don't think I've missed anything. So what's happening is, when you do that kind of stuff, I don't know what's going on. That's interesting. Okay, I don't see the same. Okay, so yeah, so this is RDF. There is this funny thing that is happening when you are very principled about building knowledge graphs. You either go straight with RDF or you rediscover RDF. So there's just no way. There is no way out. And that's really something, that's one of the takeaways for today. It's always RDF. So don't listen to marketing. That's what you need at the end. So that's the first exercise we're going to do today. We'll just expand the knowledge graph with the Straw Hat group. So that's the name of the crew, only from the live action on Netflix here. It's actually much bigger if you get further away in the series. So we're going to try to define that. And the funny thing is, we'll try to reuse notions. So you see fourth member and fourth group that are actually coming from somewhere else. It's not even defined in the one-piece universe. That's concepts that are coming from somewhere else. So let's go. I've already prepared so what you've seen earlier. So that's some RDF. The first part of the knowledge graph, Monkey D. Luffy, the friends, a bunch of them, and then the gum fruit. Everything is addressable, right? So if I go there and I click on that guy, I'm moving in the graph. This is IntelliJ with just one plugin. So, okay, we have already the notion of the graph, and now how do we talk about the Straw Hat Pirates? So think about the small sentences that we've been saying so far. So this is the subject, in a way, and we're going to say that that guy, as we've seen on the other side, is a group. Except that we haven't said yet, what is FOF? Okay, so for now I'm going to be a little bit fuzzy about it. There will be more explanation later. But FOF is a namespace. If you understand namespaces from XML, that's going to be the same story here. Okay, so now that I've summoned the fourth namespace, we'll see later it's called an ontology. Now I can actually talk about that. That's pretty cool because, boom, I can get into that other piece of knowledge that was already defined somewhere else. So far, so good. We want to give it a name. So in this case, we already have a predicate for that. So we can just use it, and then that's going to be Luffy. I'm not going to type the entire name. That's going to be the English version. And then I can start using the terms that are coming from the other ontology. It's very boring, but that's the point. And in this case, we're going to say, okay, I want to say that one of the members is Luffy, Monkey D. Luffy, I believe. Yeah, that sounds good. I'm just closing that thing. We're just going to add another one. I'm not going to do all of them. And okay, that should do it, right? Yes. Okay, so that was pretty simple, right? That's the first piece of RDF for some of you that you've ever seen and written. But yeah, there's nothing crazy about it. And that would be the full RDF in this case. Okay, so now that we have better intuitions about knowledge graphs, I think it's time to beef it up a little bit, and we are getting to the world of RDF. Okay, now this looks more like a real graph, something much closer to maybe if you want to draw it on the whiteboard, that would look like that. We have the two main entities that we've discussed so far, so Luffy and the devil fruit, each of them being their own thing. And we just have one description, the name in English for each of them. And that's going to be the example for pretty much the rest of the presentation. So very simple stuff. So what can we say about that? The first part is, maybe we should try to characterize the nodes. Maybe there's a name for them. Well, in the RDFS world, the RDFS domain, that happens to be called a resource. So and there is a specification for all of that stuff. So yeah, we have a name to talk about those things. All of them, so both the circular ones and the rectangular ones. But that being said, if we look at the rectangular one, we understand that they are a little bit different. They are kind of something terminal in the graph. We cannot really go any further. It's really a literal, just a piece of information about the resource. In other technologies, you would call that a property or a field, something like that. But here it's a literal. Okay, so we've talked about the nodes, resources, and literals. What about the arcs? What are they? Well, in this case, they are called property. And we see already, hey, that's weird. Sometimes it's RDFS, sometimes that's RDF. It could have been one. I'm not really sure why it was done that way, because they're actually codependent on each other. But property is living in the RDF namespace, but that's the name for it. And then finally, so we've talked about the nodes, the arcs, but what about we look at the node, arc, node thing itself, like that one thing, if I want to talk about it. So that's a little bit weird, right? I need to kind of step back, and I want to say, that's the one thing that I want to talk about. It becomes its own entity in the graph. So that's why I've represented it like that. And now that I have that object, somehow I can talk about the subject, the predicate, and the object that is making the statement. And that's the name for it. That's called a statement, just because in English you would make a statement about the resource. Pretty simple. So short summary of what we've seen so far. Resources is weird, actually, because if technically a resource can be, a literal can be a resource, we talk a lot about non-literal resources, which in this case would be IORIs or blank nodes. So every time, I've been using this notation with the namespace, colon, and then the term within the namespace. But if you remember when we wrote that thing, that we introduced a prefix, because we want, at the end of the day, everything to resolve to addressable terms. That was the goal for the machine to understand. So everything is either a URI. IORI is the URI you know, but add internationalization. UTF-8 is part of it. Or if you don't want to give it a name, you can use what's called a blank node. But in this case, the only way to get to that specific node is from something that is addressable. But that's still pretty useful. Properties are always IRIs. That's super important because it means that any property will be backed by something that has a definition somewhere in some namespace. That's really important. Literals, I won't spend too much time on them, but forget all the stuff that you don't like about JSON when it comes to using data in JSON. That's just not really meant for that. RDF is really meant for that. So it's very clean about having a lexical representation, which is a string. A data type will always be an IRI, which means that we can always get to the definition, and it's universal. And you have a few other goodies like being able to add a language tag, like we've been doing in this case, and even a few other things like left to right, right to left, reading, and I'm missing another one. And at the end, remember that the statement is about the SPO, subject, predicate, object. A lot of people are talking about it that way. If we go to, for example, AWS Neptune, you'll see that kind of SPO things when it comes to indexing. Because you would find actually permutations of the SPO and even a fourth part as well. We'll get to it later. Okay, so far so good. What about this strange thing? I've even used a different color for that. That's called a class. So that's actually the main thing that RDFS introduces compared to RDF. It allows you to talk about category of things. So in this case, the intent is to say there's going to be more than one character. Probably there's going to be more than one devil fruit. And these things in the graph happen to be classes. And classes, you hear class, you would think about object-oriented stuff, and kind of, but forget about that. Inheritance does not exist in that world. It's either something is a solid or not. We won't get into inference and that kind of stuff, but just remember, it is different from object-oriented stuff. Okay, that's pretty good. Like, we started with just this graph, and we've been able to say already quite a few things, like introducing more RDF stuff. But what about the graph itself? Can I talk about it as well? Well, you guessed it, yes, of course. So that whole thing, which is funny, you would expect that to be found in RDF or RDFS proper. It is not. The specifications are talking about the mathematical representation of the graph, but the best approximation is actually coming in the query language for RDF, which is called Sparkle. Here, SD stands for service description, and that's where you will find the graph. It's not perfect, but it works in this case. All right, that's what we've seen so far. I've kind of alluded to it. Sometimes I've called the thing that was before the colon. I've used the term namespace. I've sometimes used ontology. Yeah, so formally that would be an ontology that's introduced by OWL, which stands for Web Ontology Language. I know the O and the W are somehow not in the right order, but yeah, that's OWL. So all of those things would be declared as ontologies in the graph. I do like to. I think it's worth explaining that there is a slight difference between all of those terms, even if in practice we just use them interchangeably, and depending on the context, you would understand what we're talking about. So the namespace is really the idea of isolating yourself and your bunch of terms from something else. And when you put all of them together, you can form a vocabulary that can be used to describe a domain. That's somehow how that works. That's super useful as well if you attach some semantics to it or a specification or things like that. Well, you can say, well, if we agree on the meaning of those things, what emerges is a language. And if you want to be formal about it, if you want to follow some ontologies, some process or whatever, you end up just using the word of ontologies and that expressive power. So the only thing that really ontologies adds to all of that is being formal about the conceptualization. That's really that. We need to speak the same language when we are talking about those graphs. Okay, so that was all of that stuff, but there is something weird. So far, we've been able to describe things, but we haven't been able to describe the graph itself, what is expected in the graph, what the graph should look like, are there any kind of constraints and stuff like that. For a very long time, so until 2017, so RDF itself is 1999. I know it sounds pretty old. Ontology is the Greeks, 2,000 years ago, by the way. So very old technology, you can say. But somehow, the capability to describe the graphs and what shapes are in there, that's 2017, so much more recent. And that's actually the key feature, the thing that we were all missing in order to make all of that stuff usable in practice. So, same example, but now we are going up in the stack. We're going to be focusing on the small part. And the question, so now we know it's a statement, and we want to describe a little bit that kind of stuff. So we say, yeah, there's going to be some characters, and they will have a name, and that name is meant to be, in this case, some kind of string. So classes won't do it, right? We've said classes about explaining the kind of instances that can be yielded by a class. But it doesn't really allow you to constrain the shape around the characters in this case. So we need something a little bit different, which is why it's represented with a different shape in this case. And so it looks kind of like that, right? It's no longer the knowledge graph itself. It's a description of what we expect in the graph. So that's why I've been using different visualization for it. And here in this case, the arc, you can see it's no longer something that we want to assert. It's more about saying, hey, given a character, I might find at least one name, maybe 2 or 3 if I use different languages. And what I expect to find on the other side would be a literal of type RDF length string. So that's actually a data type defined in the RDF namespace. And you can see that it kind of, it's kind of the same stuff as on the other side, but it can actually describe more than one arc on the other side, more than one statement in the actual knowledge graph. So we would do exactly the same thing for the devil fruit. Nothing crazy here. More interesting, now we want to connect a character with a devil fruit, and here I've been using the predicate 8. What I think you know what's going to happen. There is nothing crazy at this point. We already have introduced the shapes for the character and devil fruit. We just have to connect them, and then in this case, we're just saying the cardinality would be 0 or 1, because some characters can eat a fruit, but some characters didn't eat any fruit. So it's not exactly optional. That wouldn't be accurate to say it like that, but kind of. Last piece. It's kind of disconnected right now, and so what's going on? What is the relationship between the losange and that is representing the shape and the circle that is representing the class? Essentially, what we wanted to say is that there is something that is targeting the class. Well, it's kind of boring, but that's the point. When these people are putting together a description of how do we talk about the shapes, they want to make it very simple to understand. So this is all about targeting classes of objects so that, really? All right, I'm going to stay here. How can I make that bigger?
F11.
Sorry?
F11.
Why is it? Is that? Can you read that stuff?
Yeah, that's nice.
Yeah. Okay. I'll do it with that. Sorry, I cannot hear you.
Oh, there's a magnifying glass right there. It might bring it apart. So where it says fit, you might be able to zoom in.
Yeah, but then, that's not what I want either. Yeah. Okay. Or. That's annoying. Okay, I have no idea why the projection is doing that. I'm sorry, I've rehearsed so many times. Okay, I'm going to go with that because it's better than saying nothing. Okay, we are targeting classes. Okay, sorry for the interruption. If you go to Wikipedia, that would be the definition for what an ontology is. And it kind of worked for us, but the language of shapes is missing. And that's essentially what we want to add here. So back to what we had before. Can we name these things? Yeah, so if you remember here, we introduced target class, and I didn't say much about it, but I've used SH as the namespace, stands for shackle. And it turns out shackle gives us a way to talk about the shapes. That's the technology that was introduced in 2017. You guessed it. These two guys in the graph would be called node shapes, so they are shackle node shapes. And if I want to talk about the combination of the properties, their cardinality, and what I expect on the other side, that would be called a property shape. And if you want to, and as you can see, right, when we were doing the lozenges and the dotted lines, they're all kind of connected. So probably in the shackle, in shackle, there's probably a way to connect a shape to a property shape. And that's actually when you use the property, SH property itself. That can be 0, that can be as many as you want. And that's the exercise we're going to do now. So yeah, so we started with that earlier. We had that description of the group. And now the question will be, can we define the shape that is actually describing that stuff? Of course we can. Okay, so I'm going to open that thing on the right-hand side so you can still see the data. And so that's the first part of the ontology. All right, so that's how you would write it. So we declare one piece. So in this case, the prefix that I gave to one piece is just in my own domain. And I can start saying things like giving a label, a comment. I can declare prefixes, so kind of bridging the gap of the gap between the syntactic world and the actual ontology world. And you can even say that one piece the ontology is defined by one piece the ontology. You can do interesting things. I've introduced already what we've seen so far. So character, remember we had both the circle and the lozenge, but in the graph they are the same thing. They just happen to be both a class in the RDFS sense and a node shape at the same time. And they have the name, 8. So far, so good. So remember, I've said that a node shape can introduce properties. So these guys here are actually property shapes, and that's how they can be addressed. So at the end of the day, they are a URI, combination of the prefix, resolution of the prefix, and the term within the namespace. And then we can start introducing the constraints. So the name, we expect the data type length string on the other side. There is at least one, so can be at least one. So n is, if it's more than one, everything is fine. We do the same for name. So there's kind of a distinction between the property shape and the property. Properties are about asserting things. Property shapes are about describing things and restricting things. 8, all right, I'll move, that was the devil fruit, and so on. The other fruits, okay, so now we're here. Let's define what a parrot crew is. So, okay, what do we want to say? Well, on the other side, well, first, this is a node shape, all right? Just close that. This is a node shape. We want to target instances of FOV groups. We are using target class, already introduced earlier, and that's going to be a FOV group. So this is saying that anytime that in the graph I see an instance of a group, I would like this shape to be applied. So hopefully this will target this instance on the other side. We can give it a name. We can do quite a few things. In this case, I'll go straight to the point. And I'll say, yeah, we'll introduce a property for it. And just by convention, it's more than convention in some cases, we're going to say that we want to describe the members of a pirate crew. Okay, so now we are connecting the node shape with one property shape. So that guy is a property shape. It's not happy for several reasons. But yeah, one thing that you need to say is what is the path in the graph that will be targeted by that thing. And here we know it's got to be fourth member. It can be actually pretty crazy. It doesn't have to be just one arc. It can be, there is a smaller language that you can use here to describe pretty much any connection between two nodes in the graph. But here in this case, the typical case is really to cover just one predicate at a time. Okay, what do we want to know? We want to know that on the other side, what we want to know is that on the other side, remember what it looks like. We want the crew to have for members characters. So that's the SH node predicate that would allow you to do that. And here in this case, we had already created the characters. And the last thing that would be missing is the cardinality, and in this case, the mean count. I don't know if it makes sense for a crew to have 0 members, although sometimes they lose battles. And so yeah, so okay, in this case, let's say at least 1. So that would be our description. Just to see, I don't know, sometimes it's acting up sometimes, but it's working right now. So if I'm saying I'm expecting at least 5, now I would see that that piece of the graph is not valid anymore because the cardinality was expected to be mean 5, and I got only 2 in this case. But if I put it back to 1, everything is fine. All right. We wrote our first RDF earlier. This is RDF again, but in this case, we are using shackle, so we're using the word of ontologies. So you wrote your first ontology as well today. Congrats. Okay, so now this is my definition of knowledge graphs. In this world of AI and ChatGPT, and you hear that knowledge graphs are going to solve the hallucination problem, they probably will. But there is a lot of marketing around what knowledge graph is, and in particular, I won't name any company out there, but some companies are just trying to sell you graph databases, for example, and that's not what this is all about. So really knowledge graphs, and that's actually very important, there are many other usages. There's a notion of graph, but you have to understand what are the nodes, what are the things being denoted by the graph. That's the most important part. The other difference with the stuff that you hear out there when it comes to AI, and that's actually very important, that's why it's going to solve the hallucination problem, is that the nodes in the graph are very, very precise. They denote actual entities, either in the real world, digital world, or something. It's not a vector that is an approximation in a higher dimension thing of some concepts out there. No, it is the concept, and it's addressable knowledge. So you can actually go back to the source of truth when you need it, which is all the time. And all of that stuff, if I stop there, graphs will be enough, but you need to be able to talk about the graph. So you need the power of ontologies, which is not something that most graph technologies would actually allow you to do. So at this point, I still want to be fair to the academic world. It would be more correct to say this is more about RDF graphs, the way that it's been described. But as we've seen, you either reinvent RDF graphs or you just adopt it from the get-go. And knowledge in this case is really about the resources and the facts in the graphs. Important thing to note, RDF graphs do not have to be serialized. I've been using what's called Turtle, which is one way to write RDF. You can use JSON, like something called JSON LD, which is just a serialization for the same stuff, it just looks different. YAML as well. That being said, it doesn't even have to be materialized. You can work on any kind of data, and if you can say somehow what it's supposed to look like in the knowledge graph, you do have a virtual version of the knowledge graph, and you can work with that. If you know exactly how to go back and forth between the knowledge graph and the underlying representation, then you're golden. You can even use your own data language and yet being knowledge graph compatible. This is not a talk about how do you query that stuff. You can do it, it's very powerful. This is not a talk about transforming that kind of data, but it's important to understand that you can do a lot of stuff with knowledge graph, not just about talking about them. Which brings me to ontologies and Netflix. So why do we even bother with that kind of stuff? All right, I cannot do that without spending a little bit of time on the problem statement. One issue that we have, so remember I'm part of the content organization, think about some of the studio side of things. And in that world, when you implement a studio, you do need a lot of very different tools. They are all sharing kind of the same data. And you want them to share the same data, but somehow that's not what's happening. Teams just end up reinventing, redefining the same kind of models. You would be surprised at a company like Netflix how many definitions of a movie there is. Well, there is a lot. So yeah, it's really, really hard to get people to just define things that are compatible, can be reusable. So that's one problem that we have leading to a fragmented data model, which is related to another part of it, which is not the first part was more the social aspect. The other part is really the technical aspect. If you are in analytics, right, your tool of choice would be something like Iceberg and the big data world, or in the middle, maybe some Spark stuff. But if you're working on applications and you are building a nice UI, or you're doing reporting, then what you care about is an API. And that's strange, right? That same movie description should apply in the two worlds, but because we're using very different tools, it's very, very hard to combine them again at the end. So how do we actually work within the same formalism that can address these two disparate worlds? Just to illustrate that, so that's what my team, that's one of the products that my team has been doing, that it's a perfect illustration of the problem. So what you see here is kind of a reduction, but it's an indexing machine where teams can actually come in and they say, okay, I have an application, I want my application, this is published on one of the many blog posts that we have on Netflix engineering, by the way. So yeah, I have an application, and my application does have some data, probably some Postgres or CockroachDB or something like that. And what I want at the end of the day is both to index some of the data, and I want to reinject that into GraphQL. So what that product is doing is just saying, okay, if you let us know about your key space for whatever you have, here using CDC, change data capture, we can essentially retrieve all of your instances. Okay, we know when they change. That's pretty useful for real time. And if you tell us what the GraphQL query is for enrichment, we can grab a lot of facts about the entity. It can even be, what's not really said here is that the edge over there is really a GraphQL gateway. So if you have even connected your entities to other GraphQL endpoints and whatever, we can actually grab a lot of facts about the entities that you care about, and eventually we can index them in Elasticsearch and re-inject that into the graph. Looks complex, but the interesting part is, at the end of the day, it's the same stuff that is flowing in all parts of the system. If, in this example, we were talking about movies, you would have a movie represented in a relational database. You would have a movie represented in Kafka. You would have a movie represented in GraphQL. Then there is Avro somewhere as well with the enriched document. And then at the end of the day, you have the mappings in Elasticsearch. That's crazy. How do we How do we get away with that kind of stuff? That's what it looks like. So it's more, if we were in the business of describing the world of One Piece, that's exactly the kind of problem we have. And that would be the good case. That's the most canonical representation of what a character would be in One Piece, either in Iceberg or in GraphQL in this side. And then you already see some idiosyncrasies from the two worlds. Okay, and I would name a table singular in Iceberg, but when I'm talking about the APIs, because there is a bunch of characters that I want to bring, all of a sudden the data would come back with a plural here. In Iceberg, I can't really talk about foreign keys. That's not really part of that big data world. All I have is just ints, and hopefully I can join later. In GraphQL, I'm lucky that I can actually federate types. I can really elevate the types into something that can be connected on the gateway. So yeah, there are things that look the same, but they are kind of different. The problem is because we are forced to work at the physical level. You pick your technology for whatever reason, and you define the schema in that world, and you're tied to that, and you stay within that world. But what you really want to do is to work at the conceptual level. There is absolutely no reason why you couldn't do that. That's what we've done at the first part, the first part of the talk. We can talk about the conceptual stuff. It's a lot more powerful. Why would you want to do that? Well, first, it's a lot simpler. There is a lot less noise. Like, you're not trying to both solve the problem and trying to see how it fits within a given implementation for representing the data. And now you can talk about things that you couldn't talk about before. If I want to say that this property here is actually a PI field, I don't have to do it both for the Iceberg table and for the GraphQL field over there. I can do it at the conceptual level, and it should apply to the two worlds. So yeah, we do want to work at the conceptual level. That's very important. How do we do that? Well, how do we unify the two worlds? You already know the answer. It's the world of conceptualization. That's why it works. Historically, what happened when all of that stuff started, that would be summarized by this slide. It's really making the case for the one schema that can both talk about things like GraphQL and Arvo and stuff like that. So there's really the idea that if there is something that I want to be able to talk about, I just have to lift it in the graph, and then I can start connecting things, and I can even start describing things that I'm expecting there. Okay. Still, we have to bridge the world. So what's going on here? How do I go back and forth between the conceptual world and the representational world? So by the way, representational world doesn't add new things. It's only capturing things that were already there. But now we can talk about them in a unified way. So if you've been in a big enough company, you've probably seen the emergence of catalogs, data catalogs. So when an organization becomes big enough, you're trying to kind of know what's out there. And what these catalogs are doing most of the time, all of the time, they're cataloging the data assets. But they're not really cataloging the really important thing, which is the data models. So we really want to understand what's out there. When I go into the data catalog, I'm not interested in looking for a table. No, I want to know where the characters are. So the cataloging aspect is something that we have to do for ourselves as well. But here in this case, we are driven by the concept. That's really the end goal. How do we allow the users internally to define the models, and how do we connect that to existing data assets out there? Much more powerful than the catalog that you have today. But the real value is actually the other direction. And that's really what we're trying to achieve. It's really saying, I want to start with the conceptual representation, which is pure. We can sit around the table, we can define that world, and then we can project it into something that is more relevant to my domain. Kind of think about, you go into the system, I'm looking for characters because whatever reason for the business I need that. But I'm an analyst, so just give me the table where that thing is, create it on the fly if it doesn't exist, I don't care, that's what I want. Oh, but I'm actually in reporting, what I want is the GraphQL API. Just tell me which piece of the schema is doing that for me. If I'm interested in things that are connected that way, maybe you can give me the actual query that I can use that will do the thing that I expect. At the end of the day, this is data. So that's the funny part. Once everything's in the graph, you're just connecting things. And it's all about describing and constructing the mappings. How do we do that? Well, that's going to be for another talk. That's my job. Yeah, we're working very actively on that, and probably in a year from now, we're gonna be able to talk about a lot of that stuff. Okay, and that leads me to the strategy that that I wanted to explain is really that's what we call ontology-first. That's what we want people to. That's the experience that we are trying to describe for the system we are building. It's three main points. The cataloging aspect, so really allowing each domains to contribute their knowledge as ontologies. That's the first part of it. The discovery and enabling the connectivity of these domains is key. And again, that's why we are using ontology for that. We don't want people to think too much in terms of data assets anymore. We actually want them to think in terms of ontologies, and then data assets will be managed for them. It's kind of an implementation detail at this point. Okay, we've been talking about a lot of stuff. We've been trying to add a lot of things in there. Where do people start? There is a big issue with all of that because it's shackle, ontologies, whatever, are not prescriptive about how to use that for a given thing. You have to do that for yourself. And what we ended up doing is, well, we had the need to really solidify a lot of these questions in yet another ontology, which is called upper. This is rooted in some semantic stuff. So we've seen properties and classes, right? The ability to say things in the knowledge graph. Then we've introduced node shapes and property shapes, so the ability to constrain and describe things in the knowledge graph. Putting everything together in ontologies. So all of those things, if you look into the actual definitions in their respective ontologies, are themselves ontologies. They are classes. They describe classes of things, like classes of properties, classes of classes, classes of property shapes, and so on. How do we constrain them? How do we describe them? Well, you guessed it. We need to introduce property shapes. We need to introduce shapes for themselves. So that's what upper is doing. So upper is introducing no new concept really, but just descriptions that we expect users to use. Not necessarily firsthand. A lot of that stuff probably will be hidden away from them at some point. But under the hood, that's really what's going on. So we want them to understand what's really expected when they describe a class or a property, what's really expected when they describe a node shape or a property shape. And in the end, what we want, the entry point is really an ontology. Okay, all of those things, like I said, happen to be node shapes themselves. Oof, that's going very meta. That's totally fine. Which means that they have been defined somewhere. They have been defined in upper. So what is upper? Upper is an ontology which happens to be self-conforming. And that's pretty cool. So there's nothing special about upper. It can explain itself. There is nothing like it, I think, at this point. Yeah, hopefully we'll be able to open source that in the next few months. Wrapping up, it's really ontologies all the way down. That's all you need. That's all you need to describe, to work and describe knowledge graphs. We've talked about RDF, really the ability to make statements about resources. RDFS introduced the way to categorize things, organizing them in classes. OWL and Shackle are all about ontologies, but really the shackle stuff is really what we care about, like constraining the graph so that we can reason about it and enabling the projections, for example. We've introduced Upper, our own ontology for describing all of that. So it's really just wrapping everything together. Depends on all of the above, for example. There is a lot more. Maybe some of you are familiar with schema.org, which is was mostly done by, I would say Google, but the other search engines. So it's really a way for websites and search engines to agree on data that is on web pages. So instead of trying to infer what's on your web page, maybe I can tell you directly, and everybody would be more happy. Very, very well supported. That's working very well. A lot of people are very interested in describing taxonomies. Trees with a root, and then we are just refining knowledge as we go down. Folksonomy, which is more about tagging, but by people, vocabularies, being able to say that these two terms are actually the same. There is a lot more again. AutoML, for example, how do I go from relational databases to RDF, so knowledge graphs, kind of the virtual world I've described before. That's something that exists. You can just investigate for yourself. Again, two main concepts that we've talked about: knowledge graphs, addressable knowledge, extremely important. So you have to think about what are the nodes. But nothing is really useful if you can't really describe what's in there. So you do need ontologies, and you need to learn what each ontology is providing to you, and not being afraid to define your own ontology. Ontology-First is really how we think about that. So scaling the authoring of ontology at Netflix, enabling domains to describe their own world and connecting that to existing worlds. And at the end of the day, abstracting away the implementation details and just getting data products, data assets managed automatically for the users. That's all I had. There's no great way to get into that world, but I was thinking about maybe these two resources are the best. Semantic Web for the Working Ontology, 3rd edition, very, very good. I totally recommend. And the other one, it's a free course, extremely good on Semantic Web. By the way, the stuff we've been talking about these days, we're calling that knowledge graphs. Before it's been called Semantic Web, linked data, RDF, all of that, the same stuff. That's what I had. Thank you.
You mind if I ask 2 questions? So first one, Semantic Web has been around for about 25 years, thereabout, early 2000s. I've found that my time in academia is more prevalent, but my time in industry is very absent. And it's really hard to convince developers who have an imperative mindset of writing code to actually transition to this type of world. How did you overcome that cultural difference at Netflix?
That's a great question. Selling RDF is never the answer. That's the trick. What's important is for people to really articulate the problem correctly. So, and that's exactly what happened. At the time when that project started, I was actually part of a more fundamental platform for data. And over there, nobody cared about that. The content organization, historically what happened, they've tried to solve that problem using GraphQL and federation 5 years ago. That's when Netflix became synonymous with GraphQL for some time. Only to realize that you can only push that thing. So developers really liked it. They understand APIs and things like that, but they couldn't really make sense of how do we bridge the gap with analytics, for example. So after trying to push the boundaries and saying, okay, let me take a step back and redefining the problem, articulating the problem, they ended up saying, oh, we actually need this one representation, this one schema. And then once you start saying that, like the solution is just immediate. Like you have to use knowledge graph, you have to use ontologies. So it's not about the solution, it's about the problem.
Right, even in that though, like there's a cultural shift in order to get there. Like when I had explained the same thing where you need to have this unified language for all the domains, one of the biggest things about ontology engineering is actually creating the ontology. It's a high effort at the beginning just to even populate the graph. It's almost like manual data entry in many cases. And that was the biggest killer for me when I was trying to propose it.
Yeah, this is what happened for the past 20 years. And I don't know, it's a mix of maybe there's not enough tooling, not enough training. I don't know exactly what's been missing, but I don't think there was a clear enough case where people were like, okay, that's what I need, there's nothing else. I know it's going to be hard, I know it's going to be new, nobody has done it before. Mm-hmm. That's why the problem statement is so important, and less so the solution. The solution should be just clear. Once you know how to articulate the problem, then you know that you have to use that. Now, the funny thing is, I can tell you, it's been a lot easier because of all of that ChatGPT stuff, because people know that there is a hallucination problem. All of the people who spend just enough time looking into that world know that, oh, it's connected to knowledge graph. Knowledge graphs are going to solve, I mean, it's a big statement. But the expectation is that that's how we can ground the knowledge into truth. And now people are a lot more receptive to knowledge graphs and RDF because of that, which is very funny because that's not what we're trying to do.
Right. So, and the last one, I'm not sure if you've noticed that, like maybe in the past 3 years, a lot of knowledge graph systems have been used in authorization, actually. So many systems that are inspired by like Google Zanzibar have been coming out recently, where they are writing the rules and all the concepts in knowledge graphs and abstracting those rules from if statements and multiple conditions that would have test for like RBAC type authorization through the system, and having a rules engine that is based on some semantic logic actually evaluate that. What is your opinion on like the recent rise of those solutions coming out, and those languages like Rego and Topaz and all of those other solutions coming out for authorization, and where do you see that going?
So I was not aware of that thing the past 3 years. Funny enough, I've done that 6 years ago at Apple internally for exactly that thing. So yeah, I'm convinced it works. I've done it. Funny enough.
Hi, awesome talk. So I'm curious, you guys have a lot of movies, like a lot, and like a lot of TV shows. Mm-hmm. And so this must get wordy. Like there just must be like a lot of data. So how are you guys, and it's in different databases, so that makes it even worse. And now the idea is to build this sort of upper layer that describes it, but like how are you guys dealing with like the performance, and I suppose maybe it's a lot of human issues too, of getting everybody to work together.
Yeah, so that's an interesting question. That kind of data is not that big.
Oh, really?
Well, yeah, it's more in terms of cardinality. When you think about it, it's more metadata. It's more the world of metadata. I don't like making a distinction between metadata and data, but it's more about, in terms of scale, it's more metadata. So in the worst case scenario, for example, data sets would be a good example. It's in the order of 2 million, something like that. Movies, there are not even 2 million movies.
Really? Okay.
No. Yeah, users and stuff like that. So it's actually pockets of classes that are pretty big, but the complexity is in describing the domains, not necessarily in handling the data. Yeah. The other thing as well is we're actually not planning to store all of that in an actual graph database. That's not the point. That's why it's super important for me, even internally, to remind people RDF is the framework. That's how we work together. That's how we describe the world. But at the end of the day, it's probably going to be stored in a Postgres, something like that. I don't even know at this point for most of that stuff. And it will be, for some stuff, it's going to be only exposed as an API, but all of it will be driven by the same kind of ontologies.
Yeah, that's cool.
Yeah. Yeah, that concerns around scalability. everyone at some point has played with graph databases, and this is too slow, and they can't even tell you what's slow, but this is too slow for doing what? I don't know. For that kind of stuff, no, you have ways, and Neptune is actually pretty good.
Yeah. You talked a lot about describing movies. Do you have to also have like an ontology of like where, like which team owns the name of a movie or something?
That's part of upper already. Yeah. It's not important for driving the projections, but it's very important to have some notion of ownership. So yeah, that's part of the bootstrapping of the knowledge graph. When an ontology is being registered in our service, you need to know who is responsible for it. Yeah, but it's more metadata about. Yeah, at the end of the day, it's all metadata. All right, if you have more questions, I'll be available for the rest of the day. Thank you.